Our introductory inventory concepts were fairly simple. We now introduce a more realistic real-world model for more demanding inventory situations. From the study guide, which see pages 385 to 396, Inventory Management. The inventory control model discussed in the previous paragraphs has one important problem. It does not take into account any variability in demand and in lead time. This does not represent the real-world situation adequately. We thus introduce a probabilistic model in which stock is reviewed continuously. This model is presented next. The model as shown has the following peculiarities. The demand is not constant but fluctuates. The lead time for orders to arrive is not constant. Stock out situations will sometimes occur as no buffer or safety stock is allowed for. Safety stock can be added later to ensure that the level of service is adequate, but does not form part of the initial model development. The assumptions of the model: demand and lead time are stochastic. Unfilled demand during lead time is backlogged. The distribution of demand during lead time is independent of the time at which it occurs. There is no more than one outstanding order at a time. The parameters of the model as listed in the textbook is listed here. The more interesting parameters is demand, the number of items needed during lead time based on history. It is presented by the average X bar D and the standard deviation sigma D. The ordering lead time based on history and represented by the average X0 and the standard deviation sigma 0. The solution for optimal Y star and R star is obtained from equations 22.6, 22.7 and 22.8 using the method explained on the next slides. These equations must be solved by iteration. If the value of equation 22.6 is calculated for R equals 0, it gives the value of Y star equals Y accent. Likewise, for equation 22.7, the value Y star equals Y double accent is obtained. If Y double accent is larger or equal to Y accent, then optimal values for Y star and R star exist and are unique. In such a case, these values can be calculated as follows. Calculate first the first trial value of Y star from 22.9, which is the simple EOQ formula. The solution for optimal Y star and R star is obtained from equations 22.6, 22.7 and 22.8. A first approximation of Y star is calculated from the simple EOQ formula as we saw on the previous slide. Using this value of Y star, R star is calculated from equation 22.7. From this value of R star, S bar is calculated from equation 22.8. Using this value of S bar, calculate a new improved value of Y star from 22.6. Repeat steps B to D multiple times until the values of Y star and R star stabilize. These are the optimal answers. Example. The cost of a single acquisition for a certain company was found to be $100. The annual demand of a certain stock item is $1,000 and the shortage cost per item is $10. The holding cost per unit per year is $2. The demand during lead time follows a negative exponential distribution with an average of 200 units. To find out if the problem has a feasible solution, calculate y accent equals y hat and y double accent equals y tilde as shown. Since y double accent larger equal to y accent, a unique solution for y star and r star exists. By applying our values to formulas 22.6, 22.7 and 22.8, we get the formulas for S bar, Y star and R star as shown here. We use the simple deterministic formula to calculate our value of Y star as our first approximation. This value is Y star equals 316 units. We now use this value to calculate the value for R star from the formulas above. This value is then again used to calculate a better value for Y star and so forth, until the answers that we get stabilize. In our case, the eventual answers are Y star equals 574 and R star equals 432. Thus, the optimal solution is to order 575 units at the time when the stock level reaches 433 units or 432 as it was calculated. This differs considerably from the simple EOQ formula, which prescribed that we order 316 units when there are 200 units left, which would have been a far from optimal solution. Next, we address methods to deal with critical spares.